Okay, so for the last talk of the day, we have Gustavo Joaquin Turiaci from Santa Barbara, who's going to give us a nice overview of JT gravity and applications. So thank you for being here, and feel free to start whenever you're ready.
Okay, yeah, thank you very much for for the invitation and for giving me the chance to talk about this in this conference. It's very interesting. Okay, yes, I will give an overview of JT gravity. In the first part, as motivation, I'm going to motivate it by studying near-extremal black holes and showing how JT gravity approximates some aspects of them. So in the first part of the talk, JT gravity will be like a tool to see what's going on with certain black holes in higher dimensions, and then in the second part, I'm going to look at the role of space-time wormholes and non-perturbative effects that will be more restricted to 2D gravity, but okay, and that's how the organization will be. But okay, let's begin with the first part. So I thought before jumping into near-extremal black holes, I would do a quick one slide of SYK model, which has been the main maybe motivation for at least the recent developments of the past, I don't know, 5 or so years. So this SYK model is a model of n interacting Majorana fermions with all-to-all interactions. And in the simplest version, it interacts by 4 fermions at a time with some random coupling, J, represented by this matrix J, I, J, K, L. And this model has disorder, so this matrix is random. It has some, well, you can assume it to be some Gaussian distributed with some mean. And the mean depends on a dimensionful parameter J that characterizes the strength of the interaction. And this is a toy model of a strange metal. It has no quasi-particle description at very low temperatures and large n, such that beta J is very large. And the special thing about this theory is that it has an emergent conformal symmetry at low temperatures, which is explicitly broken by finite temperature effects. And this pattern of symmetry breaking will be the important aspect that I will try to emphasize. And this is described at low energies by the Schwarzschild mode that will also appear later. And this is a theory that depends on one reparametrization. The degree of freedom is this reparametrization mode f of tau. Tau is Euclidean time. The action is the Schwarzschild derivative. And it has this dimensionful coupling phi r, which the name for now doesn't mean anything, but it's just a parameter. But this parameter phi r is what you should match to the UV definition of the theory, which in this case is SYK, and it has been derived with a lot of detail that this is some order 1 number times n over j. So this you should look at, you should see as the low energy theory, and there are some parameters that depend on the UV. And the relation with this with SYK is that this IR mode also appears in the description of JT gravity in asymptotically ADS2 space. Okay, but I'm not going to take this. I just wanted to have one slide to mention it, but I'm not going to go in this direction in this talk. But it's a good example to have in mind. But okay, as I said, I'm going to motivate it with near-extremal black holes. So I need to. This will be pretty much relevant to any black hole with an ADS2 throat, but I need to pick an example to be concrete. And for reasons that maybe will become obvious in a couple of slides, I will pick the BTC black hole in asymptotically ADS3. Just because it's the simplest. Well, there are certain things that one can do explicitly that one cannot do in higher dimensions. So this is the action, or at least the gravity part of the action. Here the dots could be matter or whatever you want to add besides this. But we assume that the gravity sector is described by usual Einstein theory. We want to consider near-extremal states with some large angular momentum in ADS3 and low temperature. And sometimes it might be easier to fix angular velocity instead of angular momentum, so I might go in between them as it is more convenient. Okay, and we will be interested in computing what is the prediction about the black hole spectrum and other phenomena from the Euclidean path integral. I'm not going to write the metric because I will assume that everyone is kind of familiar with BTC. But in Euclidean space, the boundary of BTC is some torus with some time circle and a spatial circle. I draw the time circle bigger because it's supposed to be at low temperatures. And this circle is becoming contractible in the bulk at the horizon, and the space circle is non-contractible, and this is the coordinate along the horizon. And I might draw sometimes the Lorentzian picture just for reference, where you have these outer and inner horizons, and this is the asymptotically ADF3 region, and this dashed line is the singularity, and all that. But I will mainly focus on the Euclidean regime. Okay, so if you have this black hole, the first thing you would do is to compute the semi-classical partition function, for example. I mean, if I want to learn something about the spectrum, I want to compute the partition function, and the simplest thing would be to do a semi-classical analysis. And the classical action in the BTC saddle is very simple. Or it has been computed a million times. And this is the answer. So this is exponential of something because it's classical. And we have three terms. And I define this variable with a notation that maybe will remind you of what appeared in the Schwarzschild, but will become clear later. We have this parameter phi r, which you should imagine what will become. And in terms of the UV data, this is the central charge over 24, so it's of order 1 over G Newton. E naught is the angular momentum, which is the energy of the extremal black hole in the classical approximation. And S naught is the extremal area divided by 4 G Newton. So is this formula. So we get a contribution about the extremal area, the extremal energy, and some small linear in temperature correction from going slightly away from extremality. And if we do an inverse Laplace transform, this is the prediction for the spectrum here. So the area of the black hole sets the overall scale of the density of states. And then we get this energy dependent contribution that is order 1 at extremality and then grows as you go away from extremality. And this formula is nothing more than the Cardi formula in a regime where the right moving dimension is very large and controlled by the spin, and the left moving dimension is small and controlled by the energy. But of course, what is right or left is a matter of convention. Here I'm assuming that this is how it is for positive J. If you would do negative J, it would change the role, but okay, that's kind of trivial. Okay, so in terms of thermodynamic quantities, this has a universal behavior that, well, my point is that this is controlled by ADS2 throat, which has this form. So the energy grows quadratically with temperature above extremality, and the entropy grows linearly. And the fact that this is quadratic, this is linear, and these two coefficients are related in this way, this is what the throat is doing, is explaining for us why this is so. And I write it this way in terms of E naught, S naught, and phi r, because this will be the general feature that for any black hole that is near extremality will satisfy. It's just a matter of finding phi r, E naught, and S naught in terms of the UV parameters. And this will be the answer for the particular case of BTC. But okay, but this spectrum is problematic at low temperatures, and I don't want to go into the reasons just because of time. But it was pointed out first, I think, in this paper from 91, that when the temperature is smaller than 1 over phi r, such that this term here is of order T, then there is something going wrong in the thermodynamic description, because emitting a single Hawking quanta will affect produce a large back reaction. And this has been, well, it appeared in a lot of papers afterwards. So there is something we expect to go wrong if we push this to low enough temperatures. And the next thing I want to say is how can we see that from the Euclidean path integral? If we don't know about this argument, how could we have realized that there is something wrong that goes on? Okay, so and this is the reason why I picked BTC. So far we assume that quantum corrections are small, but no one guaranteed that for us. So let's double check. And in BTC we have the advantage that we can actually compute the one loop correction, for example. This is something that cannot be done in higher dimensions. And the answer was computed well by Manoni and Witten, and then much more or very explicitly by John B. Manoni and Yin using like hit kernel methods. But the upshot is very simple. It's just a product of vacuum Virasoro characters that I didn't write down, but well, it's just the vacuum character of Virasoro, as a function of the complex structure of the boundary torus. So this is a function of tau and tau bar, where tau and tau bar are given in terms of temperature and angular velocity. And this is an example where it's easier to fix angular velocity than angular momentum. But okay, so well, this is a result, so we can see what happens when we go to fixed spin and low temperatures. And the answer is kind of surprising, well, maybe in a sense. And if you go to this regime, for example, within this paper, after some renormalization of what we mean by S naught and E naught, so there are some quantum effects that change S naught and E naught, but other than that, the temperature dependence becomes this. So we have the three classical terms, and then the one loop correction becomes just this 3/2 log T term. And this is kind of surprising in the sense that you would imagine that one loop effects are always small, but this, to this approximation, this one loop calculation is exact. I mean, one loop. And as you lower the temperature, these quantum effects can become arbitrarily large. And this happens when the temperature is smaller of order 1/πr, and this is the scale that was identified before. And if you, just for reference, if you inverse Laplace transform this and see, okay, well, how is the density of states modified, then you get this function here. So the overall scale of the spectrum is still controlled by the area, but the function of energy is completely different, and the exponential becomes a sinh. So from the point of view of the density of states, this is like a non-perturbative effect because this is like exponential correction, but okay, that's what it is. But it comes from a one loop effect. That's what I want to say. And when E minus E naught is very small, you can really distinguish the sinh from the exponential, especially because this is supposed to be valid as arbitrarily small temperatures. Or well, not arbitrary, at least we expect that when the temperature is exponentially small in S naught, then something new should happen, but other than that, we can extrapolate this to values where this contribution is actually large. So quantum effects become large near extremality. And this, I want to say, is the Euclidean path integral manifestation of the issues that were pointed out a long time ago. Okay, I'm focusing on ADS3, but similar phenomena happen for general black hole in other dimensions. For example, in this paper, we argue that the one loop correction in around the Rhizome Nordstrom, for example, or other black holes also has the same or very similar temperature dependence. Okay, so the general behavior for the CFT2, let's say that it would be dual, or like, well, for the spectrum of the black hole or for the holographic CFT2 has this form. And this that I wanted to, the form that I described can even be derived from a modular invariance argument. So even if you didn't know about the gravity argument, you could do a kind of bootstrap argument of the 2D CFT side, and you would derive the same. So if we go away from extremality, then you have the Cardy growth, exponential growth. I call it naive Cardy because technically everything here is Cardy, but in a different sense. When you go for temperature smaller than 1/πr, these quantum effects become large, and the way they appear is that even though in the Cardy formula you assume that the vacuum dominates, sometimes the descendants might be important, and then the answer gets modified by from this exponential to this sinh. But I want to emphasize that this is universal, or assuming that the CFT is holographic, I should have said. So I'm assuming there is a sparse spectrum, twist gap, then one can argue that this is universal for any theory with these symmetries. And also we expect this to be true for maybe the non-supersymmetric sector of 0,4 theories, for example, or something like that. But let me mention that as you go very close to extremality, the argument from the CFT only tells you that this is reliable up to temperatures that are of order 1/j. That's where there is this enigmatic phase, which is not really a problem about the black hole. It's just that there might be other saddles in the theory that, or other configurations that contribute. But if we talk about the black hole, we expect this to be true all the way to exponential small temperatures. And that raises the question of what do we mean even by extremal black hole in gravity? It seems to be a very quantum regime. But okay, yes, okay.
So in terms of things that are contributing in CFT terms, you say that Virasoro descendants are important in the region to the left.
Yeah, here.
That's descendants on the side, which is it's descendants on what side?
Yeah, on the not on the black hole side, on the dual side. So you have the black hole, you do an S transformation, and in that sense, you have the vacuum dominate. But I'm just saying that sometimes it's not only like if you do only the vacuum, it will give you the exponential. But if you include descendants on the like modular transform frame, then those descendants are responsible for this behavior here.
Yeah. So why did those descendants outcompete just some generic low dimension state? So in other words, not the identity channel.
Yeah. So for that, you need to assume that you have a twist gap or a sparse spectrum of some sort. So you need to assume that the theory is holographic. Yeah. But that's important because this is low temperature, right? So that's Cardi formula is supposed to be at high temperature. So you need some extra assumption about the theory to extrapolate this to low temperatures.
Okay.
Yeah.
Thank you.
Yeah. But that's maybe what it's done in this paper in a lot of detail, although they didn't analyze the regime where the descendants are important, but it's basically there. And they argue that if you have a sparse spectrum, you can trust this all the way down to 1/J. Although I think they didn't say it in this language, but it's the same. Yeah. But yeah, the holographic nature of the theory is important. And appearing as a sparse spectrum.
Okay, thank you.
Yeah. Okay, thanks. Any other question, maybe?
Yeah, actually, I was a bit confused because I thought that the paper by Tom and company, they were looking at non-rotating black holes. And then I have some recollection that maybe Tarek, Kanus, and some other people looked at the rotating case, and that they found that this the universal Cardi formula somehow didn't apply very close to extremality. Like they couldn't get the same constraints that the Tom et al. Could get.
Okay, I don't remember that paper in particular. But yeah, in this, okay, I didn't want to go too much into a CFT2 direction, but
okay.
Let me see. Well, they have a section in this paper about angular momentum, but maybe I don't remember too well exactly what they did. But okay, I mean, another way to say it is that actually, so the point of this paper is to do it at large central charge, but you can even work at finite central charge. And well, okay, yeah, maybe we can discuss this later because it maybe is too in a different direction that I wanted to go. Yeah. But okay, thanks for the comment. Yeah. Okay. But this spectrum looks very different from what you would expect from string. And so far we assume that we have only Virasoro, but we can look at other examples. For example, with 4,4 supersymmetry in supergravity in ADS3, which is relevant for the DUMD5 for other examples. We can look at level K. The central charge is fixed by K, and we can look at large K. And states in this theory are labeled, besides of energy as spin, by the SU2 left times SU2 right charge, which we'll call L left and L right. And they have chemical potentials C and C bar. And if we do the one loop calculation, the answer is completely different, of course, because you have different spectrum in the gravity sector. So you have a sum over saddles. So now you have saddles are labeled by an integer, and this integer labels different saddles of the Chern-Simons fields from the SU2, even though the metric is always BTC. This exponential term is the classical action on these saddles. So this is the same action that I wrote before, this one here, and then you get these contributions from the Chern-Simons that depends on the chemical potentials. And this is the one loop determinant, which, I mean, it doesn't really matter. I just wanted to show that there is some explicit formula. It won't be super important, but it has a contribution from the graviton, from the Chern-Simons and the gravitinos. And we can look at what the spectrum looks like from this. And this is how it looks like. So first, let me say, so there are two different sets of near-extremal black holes, whether they are VPS or not. The VPS black hole for positive J in my conventions can have right moving charge, but it cannot have left moving charge. So the near BPS spectrum would be a regime where we turn on the energy, but we keep the SU2 left charge at 0. And then the classical parameters of this S0 phi r are given by this formula. So this is just the C/24 I mentioned before, and this is the modification from the charge. And if we look at the previous formula and do an inverse Laplace transform and look at the spectrum near extremality, then it looks like this one here. So it grows exponentially at large energies, then it goes to 0, not as extremality, but at the finite energy that I would call the gap. And this is order 1 over phi r. And then these quantum effects that become large, actually, when you have supersymmetry, they remove all the spectrums, all the black holes in this range. So you have to leading order 0 basically here, and then you get a delta function at extremality with the weight e to the area over 40 Newton, which is what well, this is what you count in the string theory constructions with, well, when you have supersymmetry and you extrapolate from weight coupling, etc. Well, assuming the black hole dominates. So the spectrum is completely different. There is a large degeneracy e to the S0, and there is a, which is not true for non-BPS states. And then there is a gap that is reproduced at weak coupling. This is reproduced by long strings of Madsen and Saskin. And in terms of the D1, D5 parameters, this is 1 over Q1, Q5, which is the gap that is expected from. But I wanted to stress that this spectrum is derived from gravity. We didn't assume anything about strings or the microstates. And then if we look at non-BPS, near extremal non-BPS states, then this goes to 0, just like it has the same behavior as in a non-supersymmetric theory. Okay. Okay, so in all cases, we find the free energy that has this form, this classical part that is universal. This is actually the same. Well, if we look at fixed charges and not fixed chemical potentials, this always looks like the classical contribution I wrote before with maybe different identifications of these 3 parameters. And then we have quantum effects that depend on temperature in a non-trivial way. And this is a little bit more, requires more information of the theory about what is the pattern of symmetry breaking at low temperature. So if we have bosonic Einstein gravity, this has this log T, and if we have supergravity, it decays exponentially with temperature because of the gap.
So can I just ask, you calculate this from the Euclideanized theory from saddle points, right? So is there any Lorentzian picture of what it is that you're counting or getting from this?
No, not about the microstates, as far as I know.
Well, okay, but you know, if you're getting a Euclidean saddle point, I expect you're counting or estimating or doing some Cardi formula for a partition function. I was trying to get a sense of what the states are that are being counted.
Well, these are the black hole states. I mean, all the states that should be described by the black hole in the bulk.
Yeah.
I would say. If the CFT has some states that are not described by black holes, then probably they won't look anything like this. Yeah. Yeah, sorry, I don't know if maybe you have something else in mind.
I'm confused about this statement about the gap in the supergravity thing.
Yeah.
So in the bosonic case, you were just counting Virasoro descendants. Those same Virasoro descendants will be there in the supersymmetric case. So why isn't there the same effect?
Yeah, so that's what. So you have to look at the n equals 4 characters that was computed by Eguchi and Taormina, and that's where the difference comes from. So
is it some BPS cancellation of those descendants, that they come in some multiplets that cancel for some reason?
Yeah, I mean, I like this answer that I wrote here that you can interpret as a one-loop calculation. This is literally the vacuum character with it's literally the n equals 4 Virasoro vacuum character in a dual channel. That's why this 1 over taus appear.
Is it cancellation Emil, or is it lifting? I mean, okay, maybe that's the same question, but
I was just saying the same Virasoro descendants that gave rise to the log will still be there. So that must be erased by something else.
Yeah. So you have some modes that produce the log, and then you have also extra modes that cancel it. Yeah, because you have supersymmetry. And the way, so the way I think about it in terms of, well, sorry, I think maybe I'm a little slow. I should. In terms of JT, is that you can ask what are the zero modes that appear in the throat. And in the usual case, the zero or the modes that dominate at low temperature is just some part of the gravity modes. But when you have supersymmetry or a broken superconformal group, then you have extra fermionic modes. And those at low temperatures also affect the answer a lot. And they are responsible for these big changes in the spectrum.
Okay, yeah, you say it's just the one loop determinant cancellation.
Yeah.
Yeah. Okay,
Yeah.
thank you.
But yeah, from the CFT2 perspective, it's just that the vacuum character of the two, once descendants are important, and you cannot just keep only the like q to the minus c, they look completely different from n equals 4 or n equals 0. So that's another way to say.
Okay.
Thanks. Yeah, thanks for the questions. Yeah. Okay. So yeah. So what I was saying is that these quantum effects depend a little bit on the pattern of symmetry breaking, and in normal gravity we have a emergent broken SL2R broken by finite temperature effect. Here I will always assume that the horizon is at a finite distance. So I always turn on a little temperature and then see what happens when it's small. I'm never working necessarily at 0 temperature. Or in the case of n equals 4 supergravity, PSU112, which is just the supergroup with SL2R cross SU2 bosonic sector. And these features are controlled. So my motivation to why JT gravity is interesting in this context is that the low energy theory of all these effects is controlled by JT gravity in the throat and are universal. I believe even beyond the DS3 when it's not controlled by Virasoro anymore. So all this I could have derived without knowing what JT gravity is, just from only because BTC is so simple that I can do these calculations explicitly. But that might not be the case. That is not the case in Harlem. Okay, so I want to motivate JT gravity. So as I was saying, this comes from what modes are relevant at low temperatures. And in the metric, there are 3 modes that are important at low temperatures. If I expand the 3D coordinates like this, we have a metric in the TR space, like time and radius. This in the saddle point becomes the ADS2 metric, but I allow it to fluctuate with this form. Then we have the dilaton, which is the size of the S1, spatial S1, that is parameterized by phi, which becomes the horizon at some place. And then we have this U1 gauge field that is in the TR directions that is responsible, or is the one carrying the information about the spin in the metric. And then we can have KK modes that are going to become massive and are not going to affect the low energy physics. And this is basically any mode of the metric that does not have this form. And in the classical approximation, I said this metric is ADS2, the phi r is the radial direction. So this has some value, let's call it R0 at the horizon, and then it grows a little slowly as you go away from the horizon, and then it starts growing faster and faster as you go close to ADS3 boundary. And having a fixed spin means that this U1 gauge field has this form. Sorry, and yeah, this is the picture in the Lorentzian signature. So we have this big region in the middle with ADS2 cross S1 metric. Okay. So what is the action of this mode? There are 2 simplifications that I want to do. First, we can forget about 2D gauge fields in a fixed spin ensemble. And this is a simplification of 2D gauge fields. You can integrate them out easily, and if you are at fixed chemical potential, they describe the charge fluctuations, but if you are at fixed charge, they're kind of trivial in 2D. And the second one is the size of the S1 is nearly constant. So we have this, well, up to this factor of 40 Newton, this very large constant S0, which is basically the area of the horizon at extremality, and then some small, or well, not exactly at extremality, and then some small variation, which classically is growing. So there is some non-classical value, non-zero classical value for this contribution, which is slightly growing as you go away from the horizon. And this is what breaks the conformal symmetry. And okay, this is the action. So, well, this term comes from a classical contribution outside the throat. It's not too interesting. This is a topological term that gives you the contribution from the extremal area, because topologically this is a disk, so this has some value, well, for pi, so you get S naught. And then the most interesting term is this one that gives the leading varying dilaton contribution. And this is the JT gravity term. So this is where the JT gravity terms appear. And then you have corrections to this dilaton gravity, and also contributions from KK modes or matter fields or whatever. And these are either small or temperature independent. So they're not going to affect, I mean, they're crucial for getting the right values of S naught, because there can be like log area corrections or things like that, but they're irrelevant in the sense that I'm trying to focus on the shape of the spectrum. And okay, this is the JT gravity action. Okay, so finally, sorry if I took too long, but we get to JT gravity. So this is the action again, just copied. So you can ask when we look at the black hole. So let me write it. So we have something like this. Let me see, and here we have ADS2, and here crosses 1, and here we have something that goes to asymptotically ADS3. And the equation that is important is what are the boundary conditions here, and that's something that from the point of view of JT gravity we can pick whatever we want, but from the point of view of higher dimensions we need to look what are the boundary conditions here and propagate them, assuming that there are no big quantum effects far away, propagate them to the edge of the throat, see what they are. And the answer is quite natural in JT gravity language, which is to fix the metric. So as you go far away from the horizon, but still within the throat, you're kind of fixing the growing piece in the metric and allowing the subleading piece to fluctuate. And in terms of the dilaton, you are fixing the growing piece of the dilaton. And this phi r is given from the higher dimensional, is given to you by these boundary conditions here and propagating them. Or from the 2D point of view, that could be whatever you want. I mean, the throat doesn't know where it came from. But okay, so I'm trying to say that these are the natural boundary conditions. And this varying dilaton breaks the conformal symmetry, and with these boundary conditions, they can be reduced to, the theory can be reduced to the Schwarzschild, just like what appeared on the first slide. So there is a reparametrization mode that you can thought of as a boundary graviton kind of degree of freedom. And this phi r that appears here as this dimension full coupling constant that tells you when these quantum effects kick in. And you can solve this theory exactly, this Schwarzschild theory exactly, by a lot of methods. And the answer is this. So you get this classical piece. This S naught comes from the topological term. This leading linear in temperature term comes from the classical action of the Schwarzschild of JT. And then you get this prefactor that is exactly the 3 log T one loop effect that I pointed out from the one loop gravity calculation. And the inverse Laplace transform gives again this sinh of square root T. So before we got it from ADS3 because we could do the calculation exactly, but this is actually controlled just by the pattern of symmetry breaking in the throat. So whenever this sinh becomes different from the exponential, you should think that there are some large quantum effects near the horizon that are responsible for this. Okay, we can also compute correlators. So in the case of CFT2, we can insert boundary operators, which you can imagine that you integrate them over space, or you can put like a Fourier mode here or whatever. And you compute correlators. And if the time separation is large enough, then this correlator is sensitive to the throat mostly. If the time is very small, then of course this is sensitive to the asymptotically ADS3 region. So, but if the time is large, they are approximated by JT gravity as well. And the exact answer for the correlators of JT gravity, well, this is what it is. So you can rewrite it in terms of the matrix elements of the operator. Here, what I'm doing is just to insert the complete set of states and rewrite in the 2-point function in terms of these quantities. And this is what you get from JT gravity. And actually, you can give a kind of similar bootstrap argument that this is also what you get for CFT2 sinusoidal central region. So this you can show in CFT2 that is a good approximation, but in higher dimensions is a more non-trivial prediction. So this, if you had long times but not too long, then you get the classical ADS2 correlators that decay exponentially with time because of this cinch. But if you look at very long times of order 1 over phi r and of order phi r, time in the case of ADS3, times bigger than the central charge, so they are very long times, then this becomes a power law decay. So this is due to the quantum effects that change this exponential to a power. So you can see these effects. So even if you keep phi r to be as large as you want, if you wait long enough, at some point these quantum effects will become important. That's what I'm trying to say. So this is some Lorentzian calculation we can do. Well, okay, yeah. And you can also compute those time order correlators that I'm not going to go into much detail. Classically, this was computed with the shock waves in the paper of, well, several papers, Schenker, Stanford, etc. But you can also compute them exactly, including the quantum effects. This has some nice formula that I'm not going to write down because of time, with some 6J symbol.
Sorry, Joaquin, question.
Yeah.
For how large times do you expect your formula to be reliable? For example, for classical gravity calculations, we know that they can't be too reliable. Then I guess one switches to polynomial decay from the quantum effect that you found. But if I start waiting for exponentially long times, then I'm starting to get in the fully quantum regime. So can I still trust this?
Yeah, no. This is just for these times that are not exponential in entropy, but they are just of order C. Yeah. So the exponentially large times will be the part 2 if I get. Yeah. But then we have to focus on pure gravity because higher dimensions is more complicated. Yeah.
And sorry, and can you see from your analysis where the breakdown, that there has to be a breakdown of this expression at
where?
So you're saying that this expression you only expect it to hold for times of order C, but can you see that it has to break down at longer times, or
no? The breakdown, it depends on what your assumptions are, in a sense, because like you can imagine a theory where S naught is infinite, and in that case this could go on forever and there is no problem, because if you have infinite entropy, there is nothing wrong with having this decay forever. But the problem is that if you want to describe something that has a finite entropy, and then something has to happen, and then you have to add effects, and those effects are space-time wormholes, and then you can look at correlators, and those wormholes make the correlator saturate.
So the only problem, the only way that you can see that there is a problem with this is from the usual dual microscopic argument that the correlator has to be bounded by below.
Yeah, exactly.
Or it's not the gravity that is giving you an idea that.
Except that you could say that it depends what your rules of gravity are. If your rules of gravity is to sum over these topologies with wormholes, then those effects will kick in at long exponential times. So
okay, thanks.
Yeah, thanks for the question. That's useful. Okay. So this is okay. So let me mention quickly some generalizations. So we can couple this JT gravity to a BF theory, some gauge theory, and this is relevant for putting back these gauge fields that are removed. We need to put mixed boundary condition where you fix a combination of A and F, and this is actually the natural one from the higher dimensional perspective. And then reduces to a particle moving on a group. For example, here it was studied. This paper was studied for something like this for complex SYK, and this JT gravity coupled to BF reduces to the Schwarzian and a particle moving on a group with some coupling K, which plays a similar role to phi r. And this theory can be solved exactly under the correlators. Well, maybe I should have put older papers, but okay, whatever. In these papers, we wrote the correlators. And finally, you can do the same with supergravity. And this is maybe relevant to what Emil was asking before. So if you reduce 4,4 or 0,4 or Reiser Nordstrom in 4D and gauge supergravity even to 2D, you'll get the n equals 4 Schwarzian with SU2 group. And this was studied in this paper. And this JT gravity reduces to a boundary mode that is the Schwarzian again, a particle moving on SU2, and supersymmetry gives you two things. The first is that the coupling of the SU2 is the same as the Schwarzian, and the second gives you a lot of fermions that are required by supersymmetry. So this theory and the effect of the fermions and the SU2 gauge field, like you really have to include all of these new terms, control the presence of the extremal states and the large gap with supersymmetry. And these fermions come from zero modes of the gravitinos. So these two come from the metric, and these come from the gravitinos that are becoming massless because you have an emergent superconformal group in the third. And there are also n equals 1 and n equals 2 theories that I won't get into. Okay. So here I wrote the list of other applications of JT gravity, but given the time, I think I will skip because it's not super important. I mean, well, it is important, but well, probably you are familiar with it or heard of it. So, or maybe I will mention it quickly. So the first application I mentioned is to higher dimensional ADS. Then quantum chaos and OTOCs, connection with SYK. These are basically all the reference that I mentioned before regarding JT in the previous slides. That's why I didn't copy again. You can also study traversable wormholes. So this is something that JT is good for, to making explicit calculations in certain contexts that more generally will be more complicated. You can also do near and REI black holes in the sitter, where you have a DS2 throat, and then you get like a DS2 version of JT gravity. And you can do evaporating black holes. So here you can put absorbing boundary conditions, or you can couple to a bath, however you prefer. And these papers, they also, include the contributions that give the page curve, but probably this will be discussed tomorrow, so I'm not going to say anything about it. You can do holography at finite cutoff, etc., and other things. But okay, this is just a list of some things you can do with it. Okay, so this is part one. Is there any question maybe before I move on to part two? Okay. Okay, so in part two, as I said, I'm going to focus on higher topologies, space-time wormholes, and the role of disorder in gravity. And the motivating question is the following, related maybe to what Monica was asking also. But first of all, let's consider pure JT gravity. And so far the talk was presenting JT gravity as a tool to understand certain effects in higher dimensions, so even quantum and classical. In the second part of the talk, JT gravity will be a toy model, because this would be very hard to do in higher dimensions. But that's fine. And so we will consider pure JT gravity as a toy model. So we will forget about the matter, gauge fields, other terms that could be there, and just pure JT gravity. And the path integral of this theory in the Euclidean black hole can be done exactly, but there is a problem. You get a continuum spectrum, that is this sinh square root t that I wrote before, and this is not the sum of delta functions, and is not the sum of exponentials in the partition function. So this is a problem, because it's telling you that in the macrocanonical ensemble, this is kind of finite, infinite entropy states, which is not really the way we expect black holes to behave. So the goal of the second part is to review how to include extra contributions that should be exponentially suppressed in S0, that gives you some aspects of the fact that the spectrum should be unitary finite entropy and discrete in some sense. And so that's the goal of the second part, to review that. And when we add matter, this manifests itself in the fact that the correlators decay forever. And this was maybe the approach taken in this paper from 20 years ago, I guess, around that. Related to what Monica was asking, in pure gravity, we don't have matter. I mean, we can add matter, but it's simpler to stick with pure gravity for what I want to say next. But instead, we have the spectral form factor. From the point of view of gravity, this path integral with two boundaries of length beta plus it or beta minus it. And the reason why this is the analog of a two-point function, in a sense, is that if you expand this product of two-point functions in states, you get something like this that looks basically like a two-point function where you remove the matrix element. So if you were computing a two-point function, you will have here like some matrix element of the operator squared, and if you set that to 1, this is the pure gravity version of the two-point function, in a sense. And if we compute this in pure gravity, you get this forever decay as 1 over t to t cubed. while from quantum mechanics, or at least, well, maybe we have to have some assumptions about the chaotic spectrum, and actually there are a lot of noise here, but we expect something that grows linearly at some point and then saturates at some value that is exponentially small in the entropy. So the question is how to get something like this that would come from quantum mechanics. Maybe I should have read the quantum mechanics with a finite entropy. That's important. If you allow the thing to have infinite entropy, then there is no problem. Yeah, sorry, what?
You wrote something about the gravity. Does this thing have the same problem as ADS3 pure gravity of negative degeneracies and stuff like that, or what's the problem with the partition function?
Yeah, this is a different problem. So in pure 3D gravity, you have negativities near the edge of the spectrum that can be resolved in some different ways. But even if you do resolve them, you still have the problem that the spectrum is continuous, and then you have to solve that in some other way. And this is the analog of trying to solve the issue that the spectrum is continuous.
I see, but the two-dimensional partition function, does it have any sort of negativities or also? In
JT gravity? No.
Yeah, in JT gravity.
No, well, you can do something which is JT gravity with one defect. Okay,
I see. So the question mark in front of your after your Z gravity is simply because the density of states is continuous. Therefore, you don't know how to interpret it.
Yeah. So JT gravity is simpler. It doesn't have this problem. Or at least pure JT gravity doesn't have this problem of negativities. But you can cook up examples of JT gravity with other things that could produce negativities. For example, with one defectors, and then which you can make to be analogous to the pure ADS3 case. But okay, yeah, in ADS2 there is no problem of negativity.
Okay, thanks.
Yeah, thanks. Yeah, the issue is the fact that the spectrum is continuous. So I saw there was some message in the chat. I don't know if you want to ask or what.
No, that was some wrongly directed remark.
Okay, thanks. Okay, yeah, so I guess I should hurry up a little. So yeah, as I was saying, so what effects, the interesting question is what effects do we need to add in gravity to get this behavior, that these exponentially small effects that should fix this problem. And the proposal of Sachenko and Stanford was to sum over topologies. And these sum over topologies can be interpreted as some space-time wormholes. So these are Euclidean space-time. So this is a space-time wormhole. In the case of one partition function, there are configurations like this or with more handles. And in the case of the spectral form factor with two boundaries, you have to add, this would be the leading contribution. You need to add these wormholes connecting them, or also some wormholes like this and all things like that. And the proposal of this paper is that after you sum over all this, you get some resemblance of a solution of the issue I mentioned before. This will revive an old aspect of wormholes and the possibility of having holography with disorder. Okay, so the surprising feature of this theory of pure gravity is that can be solved exactly. Well, maybe it's not too surprising, but it's kind of non-trivial. In order to do this, the first step is to do a topological expansion. So this is very natural. So we have n boundaries, and we sum over contributions of fixed genus. That's all that topology means in 2D, anyways. And these contributions are suppressed in S0 exponentially as expected. So we want something that if we send S0 to infinity should go back to the previous discussion. This does it. So then we need to compute these contributions at fixed genus and fixed number of boundaries. And to compute this, we first integrate over the dilaton. If you remember, the theory has linear dilaton, so it just imposes a constraint that basically the curvature is constant and negative. And then the sum over these surfaces simplifies. So first we have a contribution of, I should say first, for when you sum over hyperbolic surfaces, it's a fact of geometry that all these boundaries have a geodesic that is homologous to them, that you can find such that there is no non-trivial topology between the holographic boundary in the geodesic. So there are no wormhole here, or if there was a wormhole here, there would be another geodesic here. So that's the point. And then we can separate the space-time into this bulk piece bounded by geodesics, and then the other pieces that glue to the holographic boundary. And in a sense, JT gravity is tree-level exact, in these surfaces, which means that the one-loop determinants are trivial. So when we sum over geodesics, we just roughly compute the volume with the Weil-Peterson measure. Which the Weil-Peterson measure is what you get without any extra one-loop correction. This is not true for unoriented surfaces, which was studied by Stanford and Witten. So the first thing we need is to compute this. And then the second thing is to compute these trumpets and the contribution between the geodesic and the holographic boundary. And this is easy to do. Basically, the theory reduces to a deformation of the Schwarzschild mode living here. And that can be computed exactly, it's one loop exact, etc. And it's a very simple function. So this is a simple function. I didn't write it down, but this is a known simple function. This is a complicated thing that we don't know what it is. But okay, and then the last step is to glue. And the way to glue it is to fix here the geodesic and integrate over the length and also the twist, because you can glue them in different ways. And this is the correct measure after you do this, which comes from the Weil-Peterson measure. And this factor of B1 comes because of the freedom to twist the circles before gluing. And then you need to integrate over all these geodesics. So this is a very simple answer in some sense. So this is the exact contribution from pure gravity in terms of these trumpets that are simple and these Weil-Peterson volumes that are complicated. The answers are fixed in terms of Weil-Peterson volumes in the previous formula. And even though we don't know them in general, we know that they satisfy a simple recursion relation derived by Mirzakhani some time ago. And this is easier to write in terms of a different observable. So we are interested in this, but it's easier if you do an inverse Laplace transform, a Laplace transform, and write it as this function W in terms of Z1 to Zn. And this is where Z is the Laplace coefficient. Well, this simplification actually was pointed out by Einard and Orantin, that if you write the volumes in terms of this W, then this W satisfies this recursion relation, where the WGN is given in terms of Ws with either less number of boundaries or smaller genus, such that this is actually a useful recursion. And it requires two seeds for the recursion, which is the 0,1. This is no handles and one boundary, so this is the disk. And it has to have Mirzakhani's recursion requires this initial value for that. And this value for the cylinder, which has 0 handles and 2 boundaries. And this is precisely the density of states of JT gravity, and you're supposed to identify Z with energy in this way. But okay, Einar and Orantin wrote the recursion in this way and immediately realized that it's equivalent to the one derived from the matrix integral loop equations. And in this interpretation, the W's are correlators of resolvants, where again the energy is related to Z in this way. And once you know this, then Sachenko and Stanford realized that this density of states that appears here, that defines this matrix model, is the same as the one that appears in JT gravity in the disk. And also you can match the cylinder as well. Then they concluded that the Euclidean path integral of JT gravity, when you sum over wormholes or topologies in this way, is computed by a random matrix. And this is the relation. So this is the relation for the volumes, but if you ask what is the relation between the matrix resolvants and the ZGN, the partition function, then this is what it is. So this is the matrix model resolvants, and these are the JT gravity Euclidean path integral answers. But okay, maybe this formula is not super illuminating, so this can be written in a nicer way, where I will repeat what I just said. So pure JT gravity, SSS showed, is equivalent in a holographic sense to a double-scale matrix integral, such that, well, this is true. So the partition function computed in gravity as a function of beta is the same as first pick a matrix H and interpret it as a Hamiltonian with size L by L, and L is of order e to ds naught. Well, you have to take the double scaling limit, but I don't want to spend too much time with that. So then this term is interpreted as the partition function of a quantum mechanical system of Hamiltonian H. And then you need to integrate. So if we were doing usual holography, you would end there. Like you would have some particular value for that big matrix. Maybe it's very complicated, but it would be some concrete numbers. But in what we observe in JT gravity is that you actually need to average over Hamiltonians. That's what this integral does. So JT gravity is dual in a holographic sense to a disordered theory or an ensemble average, or however you want to call it. And the probability distribution, we assume to take for JT gravity, it takes the usual form of, in terms of a matrix potential. You could consider more general functions of a matrix, but happens to be this simple one that reproduces JT gravity. And this matrix potential V of H is fixed in terms of the fact that to leading order, the disk should give the sinh of square root T. And more generally, you can compute this. So if you have several boundaries, you're instructed to first compute the partition functions for a fixed Hamiltonian, take the product, and only then average over Hamiltonians. Okay, so this phrase is something that is called the factorization puzzle, and I put it in quotes because I'm not sure if it's really a puzzle or just a fact. That was maybe, I think it was first mentioned by Witten and Yao in '99, but I'm not 100% sure. So you could ask, is there what is the simplest quantity that would tell you that the theory is dual to an ensemble of theories and not a pure theory? And so the smoking gun for holography with disorder is this configuration, this wormhole with two boundaries. Because here, since we have to average over Hamiltonians, there is nothing that guarantees you that the partition function with two boundaries will be the same as the product of partition functions with one boundary. So that's so if you want to have a theory of gravity and you don't know if it's an ensemble or not, this is something you could compute. Of course, it's hard to compute, but okay. So I don't know, depending on your opinions, this might be a problem or not, because this seems to be not consistent with the black hole seems to not be described by quantum mechanics, but by some average of quantum mechanics. The possible answer is to add baby universe Hilbert space. So you enlarge the Hilbert space to put the theory in the framework of a larger quantum mechanical system. Which, well, this was explained a long time ago in the context of wormholes, but it was spelled out more recently in the context of recent developments of the information paradox. But in this paper we point out, I mean, and this is, well, might be correct or not, that this picture of the larger Hilbert space does not necessarily always work in the right way, and it seems like the wormhole is telling you not that you should do this enlargement of the Hilbert space, but it looks something closer to a classical average over quantum theories, which is not necessarily the same as a quantum theory. So, but okay, this is hopefully will be understood better in next years. Okay, so let me finish very briefly. I guess it's almost 1 hour, right?
Yeah, it's been almost 1 hour, but you have 1 hour and 15 minutes, so you're still free to continue.
Okay.
But considering you also have some questions later on.
Okay. Yeah, I'm almost done anyway, so okay, I will take a couple more minutes. Okay. Yeah, I want to leave some time for questions. So, okay, so yeah, the last thing I want to mention is just some generalizations of this idea, of this duality between black holes and disordered quantum mechanics, if you want. The first generalization I wanted to mention, well, I noticed this morning I forgot to put, well, there is a first generalization that was done by Stanford and Witten, which is to consider some over unorientable surfaces and also theories with supersymmetries or theories with fermions. So that's one generalization you can do, and then if you have an oriented surface, instead of a integral over Hermitian matrix, you get like a orthogonal ensemble or symplectic ensemble. But okay, second generalization is for theories of dilaton gravity with more general dilaton potentials. So that what that means is that if you ask what is the most general theory of dilaton gravity with two derivatives, then it has this form with an arbitrary function of phi. And you can ask the question, is this always dual to a matrix integral? And the fact that in the matrix integral you have a free function, which is the matrix potential, And here you have a free function that is the dilaton potential, should make you think that you should somehow be able to identify the two, and that happens to work. So that has been done for potentials of this form. So there depends on these parameters lambda and alpha. And this, well, it was mainly done in these two papers. And this is some preliminary calculations, and this is some extension for, well, larger ranges of values. And this requires two things. The first is to find the new density of states in the disk, namely to solve this theory in the disk exactly. That's something that has to be done. Otherwise, you don't know what the matrix model is that you want to compare with. And once you do that, once you solve it and find this function rho, and this is where issues like what Monica was mentioning appear. So you can cook up examples where you can have negativities when you include these more general dilaton potentials. And then you have two problems. You need to somehow solve the negativities and also solve the finite entropy issue. But after you find this function and you see that it has good properties, or you decide when does it have good properties or not, then you need to show that higher genus corrections follow from a matrix model recursion with this particular seed, or well, with this matrix potential associated to this density of states, and that can be checked explicitly. So that's one personalization. Second generalization is that you can also add to these two theories of 2D dilaton gravity coupled to gauge fields, and they are still dual to matrix integrals. Here, what you have is a matrix that you should imagine that a matrix with different sectors that transform in different representations of the group. And then each of these sectors are statistically independent, and that's how it works. You can also add matter correlators, and this was done, well, some was done in these two papers, which kind of answers or addresses the question that Monica was asking about the 2-point function. So you can see that these effects are going to kick in when you wait times exponentially large in the entropy. And the last thing is that this limit is also a limit of the more familiar duality between non-critical strings and random matrices. There has been a lot of paper. This was already pointed out in SSS and then expanded in several ways. The only thing I want to point out is that I find interesting mostly is the fact that in the old approach, the matrix came from triangulation of the space-time. This is, so I took this picture from the review of Ginsberg and Moore. So the matrix comes from this triangulation. So when you take the double scaling limit, this triangulation becomes generating something that resembles a continuum surface. But the new concept maybe from SSS is that this matrix also plays the role of a holographically dual random Hamiltonian, which I think is a new twist to this story. But it's interesting that the same matrix that controls the boundary quantum mechanics is also responsible for somehow making up the space-time inside. So that's it. Yeah, that's fine. Interesting. And okay, and there is some evidence of similar phenomena in ADS3 gravity where you can have disorder. It's not some, yeah, okay, where you can have models of ADS3 gravity that hint towards being described by an average of CFT2 in this paper, but you can also have concretely examples where you choose how you do your average over 2D theories, and then realize that they're described by some sort of gravity theory in the bulk. So that's something one can also do. Then maybe, well, the last example I wanted to mention the sitter quickly, but maybe I will just say that when you study DS2, there is a similar correspondence between the Hartle-Hawking wave function for creating a universe of a certain length and a similar matrix integral, but the interpretation is less clear. But okay, maybe I'm already talked for too long. So okay, so these are the conclusions. So I'm done. So JT gravity is it's very useful. First, to understand the spectrum near-extremality of black holes in higher dimensions, whether there is a space of extremal states, what is the size of the gap, and toy model for, and also describe some processes like the onset of chaos, shock waves, traversal wormholes, these quantum effects, this modification of the Hawking spectrum and these quantum effects at late times, but not too late. And also useful for studying space-time wormholes contributions, responsible for recovering some aspects of unitarity of the spectrum, and there will be probably more said about this tomorrow. Yeah, and finally, one can also study some toy models of the sitter, and the implications are still interesting to analyze. But okay, that's all. Thank you very much for your attention.
Okay. Thank you very much. Thank you. Let's thank Joaquin for a very nice talk. We had some questions in the middle, but I think we have some time. We have quite some time for further questions. So I think Nick, if you want to start.
I think Emil was in front of me, but okay. Yeah, no, okay. I had a quick question. If you go to 0.4 or 4.4 versions of this JT gravity, is the sort of corresponding matrix model and the whole matrix story worked out for that, or known even what the matrix model is? Someone thought.
Sorry, I didn't hear the first part.
If I extend JT gravity to a 0.4 super JT or a 4.4 super JT, is the matrix model story known for that?
Only for, yeah, that's an interesting question. Unfortunately, only for n=1. That was done by Stanford.
The reason why I'm laughing is that was always the issue with matrix models 30 years ago, whatever it was, 1990s, when Ginsburg was writing a review. Adding more degrees of freedom, you ran into this C hat = 1 barrier or something. Yeah. It's very hard to add extended supersymmetry. So
yeah, exactly. Yeah. So that's it. Yeah, going from 0 to 1 is much easier than from 1 to 2, or even more than 1 to 4. I don't know, but it would be nice.
It's not just a case of doing some clever matrix ensemble that you have to use, like orthogonal or symplectic or super symmetric matrices. Is there some algorithm there?
No, it's something. If there is something like that, it's more complicated. Yeah, I don't know. It doesn't seem to. So if you look at all the ensembles, they're all saturated. Like you can find a theory of gravity that describes all the ensembles, which was done by Stanford and Witten. They explored like, what are the all possible ensembles you can write and of matrices? Can I match them all to some theory of gravity? And I think they did that. So the whatever is the dual of n=4 super JT has to be something different. And I think it would be very interesting to. If that would, the problem from my perspective, I think, is that, well, first of all, JT gravity is simpler than the minimum string. So that's something that maybe it's simpler to study than these older dualities. But the problem is that I don't think there is much information about these volumes of hyperbolic surfaces with that much supersymmetry. But okay.
And the added structure of all the other degrees of freedom.
Yeah.
Yeah, sounds like the same brick wall they ran into 30 years ago. Okay, thank you.
Yeah, but the theory of gravity is a little simpler, so maybe one can do a little bit more progress with that. I don't know. Yeah, that's open question for me.
Thank you.
Okay, Samir, would you like to go next?
Okay, yeah. Thanks for that nice talk. I just had the following question from the first part of your talk. What it looked like was, if I take 3D gravity, let's say gravity, the BT black hole in ADS3, and I just dimensionally reduce on the angular circle phi, then I can start thinking of it in the 2D gravity language. And then the fact that there are no propagating degrees of freedom in ADS3, in 3D gravity, that becomes the fact that in JT gravity, you only have this boundary degree of freedom given by the Schwarzschian. Is this correct, at least so far?
Yeah.
So is there any advantage to thinking of things in the 2D language? I mean, the 3D language, if I'm happy to work with 3D, it just looks more geometric to me. So I could equally well do that, right?
Definitely, yeah. My point was different, was that, so you can work with the 3D language, and I like the calculations that I did in the beginning were in the 3D to motivate 2D. But then you can look at examples where you cannot do things like you do in ADS3. So let's say you have a black hole that has no ADS3 factor in any part of the geometry, but you still have ADS2.
Right.
And that is my point, so that the ADS2 is more universal than ADS3, because you can imagine near-extremal black holes with ADS2 that do not have ADS3 anywhere.
Okay.
So that's, but so if I was able to like compute these one loop corrections in higher dimensions with no ADS3, that would be great, and then one can match. But it's a calculation that is hard to do.
So if you also add back the supersymmetric degrees of freedom, like you did the n=4,4 that Nick was also asking about, and you mentioned that, You're looking at all that in the Euclidean section or the Lorentzian section?
No, mostly in the Euclidean, to use the Euclidean path integral to compute the partition functions like, I don't know, Gibbons-Hawking. Yeah.
So would you say that if you had, okay, good. I understand. I think that's exactly what you were doing. But if you have the n equal to 4-4 supersymmetry added back to, let's say, 3D gravity, or in this case, the 2D reduction of 3D gravity, what are we losing which would take us over to the full string theory?
Well, in the theory with supersymmetry, well, I guess matter. I guess, like, I mean, you will have a lot of stringy modes that you should add to this theory that maybe will affect the answer when you go to low enough temperature, or
yeah, I'm just worried the theory may not be consistent, because the entropy works out correctly, as we know from the Euclidean section, without even worrying about the full 10-dimensional string theory. But the actual microstates are not there, right? You need Strominger-Waffer to get the correct microstates for the 10D theory to account for that entropy. So I always thought that anything like the 3D theory or the 2D theory was basically inconsistent or incomplete, maybe at a one-loop partition function level. And if I actually force myself to make it complete, I'll have to go back to the full 10D string theory anyway. Would you agree with that line of thinking?
Oh, yeah. Okay, I'm not sure. I guess, yeah, I was assuming that if you start from 10D, then you go to the throat that is ADS3 cross S3, and then you have some reasonable definition of what ADS3 CFT2 means. You have some 2D CFT describing that black hole. But you're saying that maybe that's duality is not well defined without realizing that it came from 10D.
That's what I'm worried about, because the entropy of black holes can only be counted correctly in Strominger-Waffer using all the extra dimensions. But of course, the entropy can be reproduced from the Euclidean geometry in 2D or 3D. Yeah. But the actual states really come from the other dimensions.
Yeah. Well, I guess in the case I was looking at, I mean, for example, having the S3 is definitely important, right? That in the supersymmetric case, that's where the SU2 comes from.
That's right.
So that's one example. Like if you have ADS3 with like a small extra ADS3, so maybe your question is if you, or maybe you're pointing that it might be inconsistent to have ADS3 with small extra dimensions or that don't.
Yeah, something like that, maybe. Yeah,
something like
that's the question I was really heading for when I said, okay, you've got these cool Euclidean saddle points, but what is it that they're counting in the Lorentzian regime? I think, Samir, are you heading in that direction? You're saying, okay, the only way to count this in the Lorentzian regime is to go to string theory or whatever and count strong.
Yeah, that's what I was wondering. I was just wondering what all we have lost by looking at JT gravity. And if we have lost anything, it doesn't show up as an inconsistency of the JT gravity at some one loop level. But I think, yeah, I think he answered whatever I was asking. So it's good.
Yeah, I'd actually like to follow up on that. So I think I understand what the zero temperature extremal black hole is in that context, right? It's just the states that contribute to the elliptic genus. And so there are supersymmetric ground states, say, on the right movers, and then your favorite excitations on the left movers. And so, but you were always insisting, I really want to think about a situation where I've excited the system to finite temperature, and I take the zero temperature limit. So you're actually looking at some ensemble of states where you've also excited the right movers a little bit, just the left movers are excited, you know, to some extremely high level of order, you know, C. And right. And then you said the one loop fluctuations come from some Virasoro descendants. Are they descendants on the right, on the site which has low excitations, or descendants on the left, which has high excitation?
No, the one that has low excitations.
The one that has low excitation. Okay.
If you look at corrections from the one that has high excitations, then they produce things like log area corrections that are temperature independent, for example. Kind of logarithmic corrections to the square root J, and I think Maybe I should have mentioned it, but yeah, I think those corrections are probably the ones that are correctly computed by Sen and papers that came after, where you look at corrections that are temperature independent, that are logarithmic, but don't affect the shape of the spectrum. But okay, whatever. So maybe I'm going.
Yeah, and so is there? I guess what I'm kind of fumbling towards is in what sense there's a decoupled theory here, or approximately decoupled theory, from the point of view of CFT2.
Yeah.
It's like one is saying there's some approximately decoupled subsector of CFT2 if you go to this limit of highly excited on the left, not so excited on the right. And
well, yeah, I don't know if that's what you mean, but I mean, obviously there is an issue with taking the decoupling limit of black holes with ADS2 throats. So you can do it with ADS3, kind of take a decoupling limit of the higher dimensional picture. But in ADS2, you cannot really take a decoupling limit in the sense that you have this problem that things at exactly zero temperature are a little singular, right?
Yeah. So it's not exactly ADS2, it's nearly ADS2 and blah, blah, blah.
But the difference with higher dimensions is that when you go a little bit away from extremality, you think, oh, this is some irrelevant deformation. If I take zero temperature again, they are kind of small. But that's the problem of ADS2, is that that's not how it works. It's like you go a little bit away from extremality, you think you did some irrelevant deformation, and then you go to extremality, and these effects become large. So you can interpret that as an issue, saying that there is not really a well-defined decoupling limit of ADS2 within the ADS3 or within the higher dimensional black hole, that whatever black hole you're studying with an ADS2 throat. I don't know, maybe that's not what you're asking. Because, I'm imagining that maybe the decoupling you have in mind would be to identify what are the quantum mechanical degrees of freedoms in the CFT2 that make up this black hole. Sorry, what are the degrees of freedom in the?
So decoupling is probably too strong a word. I mean, because there are power law, there are corrections away from the ADS2 geometry which affect the asymptotics, and they're precisely the asymptotics that roll the ADS2 over into ADS3. But nevertheless, I think one has the sense that the heart of what's going on in the bulk is the physics near the horizon, and that's way down some long redshift. So there should be some sense in which what's going on down there is insensitive to what however you rolled over things to ADS3.
Maybe that's what I was trying to say, that seems to be a counterintuitive thing of ADS2, that it doesn't quite happen, because there seems to be these large quantum effects that that appear when you try to go a little bit away from extremality, which you would think as going a little bit away as some effect that comes from the glue into ADS3 or I don't know.
Let me rephrase the question this way. So the picture I always have in the back of my head is there's some ADS3 geometry which is coming in like this, and then at some radius which is basically where the S1 stabilizes, it now becomes a long ADS2 throat with the S1 now having, the S1 is just the azimuthal direction of ADS3. So of course in the ADS3 regime, it's growing exponentially as I go out radially, but then I reach some radius and it stops shrinking and reaches some finite size, and that's my ADS2 throat. Okay. Now, I think you were saying this during the first part of your talk that, there are some things that in the ADS2 gravity I would consider boundary correlators, or boundary observables, right? Where I stick in some observable on the ADS2 boundary, it has some OTOC or whatever, but that's something purely within ADS2 gravity. Now, I think a consequence of this map is that there should be some collection of observables within ADS3/CFT2, which are the representatives there of the computations that you were trying to do in the ADS2 theory.
Yeah.
And so the question is sort of like, what is that class of observables? And is there some sense in which their correlation functions are dominated by what's going on deep in the ADS2 throat?
Well, yeah, that's something we can show. Let me see. I mean, that's something we can show. So yeah, I had this picture that here is the ADS2.
You had this picture of like geodesics running down the throat and coming back up and so on.
Maybe like this. So yeah, they kind of go like this, and somehow here is the horizon. Yeah, so I'm imagining here that I'm inserting the operators in the ADS3 boundary. So here I have some and you can show at near extremality. There are some nice papers by Trivedi also, but okay. That this correlator computed in CFT2 is equal up to some prefactor to the one computed in ADS2. And so this is something you can actually show, like the contribution from. So what you do is to study what is the contribution from this part, and okay, maybe assume that there is no any quantum effect or anything funny going on here. And the effect of this region is just to basically like renormalize the overall prefactor of the. So here you get some function of the dimensions, or like they're literally proportional to each other. And so then you can compute the correlator in ADS2 with some particular mass. Well, you get some field that has some particular mass as a function of the scaling dimension. And then this thing is the same as the CFT2. And when, so in what you can do is to give a bootstrap argument of CFT2 that this is true, like even without knowing that you have this throat and this gravity calculation, you can do a bootstrap argument in 2D CFTs that the correlator has to have a certain form controlled by the vacuum intermediate states in some dual channel. And then you can write that answer and realize, oh, this looks exactly the same as the ADS2 correlators up to some prefactor. And this prefactor matches with the contributions from these parts of the asymptotically ADS3 regions.
Okay, and sorry, who did you say did this calculation?
Yeah, we did it in a paper with Gosh, with Henry, and myself. Yeah, from 2019, I think.
Sorry, that's not showing up. Okay. Okay, great. Thanks.
Yeah. So okay. Yeah, there is a very specific relation between the ADS2 and higher dimensional correlators.
Very good. Thank you.
Yeah, sure.
I had a question.
Okay, I think so. Sorry, go ahead, Yusuf.
No, it's just, I mean, I think as a comment to Samir Mathur's point that, the JT gravity is not a complete theory and so on and so forth. We know that, for example, in ADS2, essentially, if you want to do perturbation, if you want to put something there, you have two choices. You either glue it to ADS3 in the UV and then, you can do stuff, or you can cap it in the infrared. And in a sense, we have a huge amount of solutions, which are microstate geometries, which are basically have a huge ADS2 throw to the cap. And those have excitations, they're very, very happy. So in a sense, ADS2, but okay, in JT gravity, it's very hard to see those because, JT gravity doesn't see the capping. In JT gravity, it's impossible to see the capping, but there should exist some two-dimensional theory, some 1 + 1 dimensional theory, which is JT gravity plus some extra fields, where this capping should be visible. And there, I think that theory is going to be much more universal than JT gravity. In particular, it will be describing a huge amount of degrees of dynamics inside the ADS2, because for example here when you have this ADS CFT correlator like this this CFT when you have this correlator between two operators in the CFT1, that correlator cannot depend on time, right? I mean, if there's a conformally invariant ground state, you can show that the theory is topological, and yet we know very well that
sorry, can I make a quick comment? Yes. But something important in this story of the nearly ADS2 and this is that this only makes sense after you break a little bit the conformal symmetry explicitly.
Yes.
Like for example, just to mention, the classical limit that you get that the density of states goes as like, well, what I call phi r square root, square root, for example, right? Like you clearly see, if you want to reproduce anything like this, that you need to break, like you're introducing a scale, right? So this is not the density of states that you would expect from something that preserves the conformal symmetry exactly.
But you can do it, but the point is you can preserve the conformal symmetry either in the infrared or in the UV. And if you preserve it in the UV and you just keep an ADS2 boundary conditions in the UV forever, you can break the conformal symmetry in the infrared by just capping the ADS2. So you have an ADS2 which goes and then ends in a smooth cap. And then you can get exactly the same. And then by binding it there, you can actually put perturbations there, and you can have you can really build states, inside these capped ADS2s. And those states, they're going to give you, they'll have growth and so on and so forth. So you don't need to break the density of states by gluing to ADS3 and by going to non-extremal. You can stay supersymmetric. The only price to pay is that you cannot stay in JT gravity. You have to basically add some extra fields in order to be able to get this capped geometry with a cap in the infrared.
Yes. Let me see. Yes, but yeah, okay. Yeah, that's true. I mean, the reason that you need to go a little bit away from extremality and you have these corrections are because otherwise ADS2 is not well defined at exactly zero temperature. But and so if you look at supersymmetric states, then maybe the surprising thing is that supersymmetric states seems to be fine because you have this delta function here that you can interpret as something.
And those in principle you can also build them. So in supergravity we have we have a huge amount of superstrata which are exactly what you do. I mean they're basically asymptotical ADS2, and they have a cap, and there's a huge amount of them, and they give you they give you all the right excitations. And then if you put perturbations on top of them, you see that all of them are gapped, and the gap is over the 1 over n1 and 5, which is exactly the one which you find.
Yeah.
But
maybe,
yes.
Sorry, maybe a question I have is that there's also an argument. I don't know if Monica is still there, but which that from a CFT2 perspective, this shape of the spectrum is pretty, or maybe under some assumption is universal. And if you don't have supergravity from the perspective of JT, it seems like there is not really a good regime where you can assume any conformal symmetry. But so okay, here is broken. But also this shape of the spectrum that you reproduce, or maybe my question is, can you reproduce this shape, or like the part of this shape that is universal? Can you reproduce it for?
No, that's very hard. The only thing we can reproduce, the only thing if you go to the next page, I mean to the page where you had this delta function at the origin.
Yeah, this one, yeah.
So you can reproduce, so you have all the states at the origin, and then and then the gap you find again by doing this nice calculation. It's also, you can also find it by just doing supergravity, by just solving supergravity on top of this superstratum solutions, and they come exactly as a tower, and there's an E gap which is the same as the CFT E gap, and then you start having states. You see that the states start growing around after this E gap. That much is, and there's a minimal place, there's an interval above inside which there are no states. I mean this is something which we can see using this cap geometry also.
Yeah, and it's like a classical calculation in this.
It's a classical calculation, absolutely, but it's a classical it's a misleading classical calculation because there's a throat which has a length which is actually over the 1 over n1 and 5. So there's a classical calculation in a throat which has length n1 and 5, and it comes out as and the gap comes in from just solving the classical equations of motion as 1 over n1 and 5. Now in ADS-CFT you interpret that as a quantum result, even if it comes from a classical geometry, and that's happening because you have a very long throat.
I see.
I think Samir's got his hand up, by the way, guys.
Yeah. Is there a question?
So
I think this is this might be just a remnant from before, but
yeah, I just took it down.
Okay.
Yeah, a quick question maybe for what Chief was saying is, so even without going to the non-supersymmetric case, we also observe a similar spectrum in the. Well, my question is, do you see the same gap for non-BPS extremal states?
Anything which has an ADS2. So the point is, if you just look at the ADS2 and you just pick up your random microstate geometries, the moment you're in asymptotical ADS2 with a cap, you always have this phenomenon. Now there's a caveat, and the caveat is that the only way we know how to build these states is by looking at this almost BPS example, which is also known as the Goldstein-Katmadas ansatz. But there, when you go to the ADS2 limit, even if your black hole is not supersymmetric, the black hole is like a D1, D5 P with an anti-KKM. D1, D5 P KKM is supersymmetric, D1, D5 P anti-KKM is not supersymmetric. So the black hole is not supersymmetric when in flat space. But when you take the neo-horizon limit, you get the same supersymmetric ADS2. So in a sense, you know, you can say that the original black hole is not supersymmetric, but on the other hand, the theory in the neo-horizon limit, it's all the same as the supersymmetric one.
Oh, but that would be like, yeah, so I was mentioning here, it would be like a 0.4 kind of example where like you're exciting the modes that are not supersymmetric, something like that. Yeah, those ones, according to I don't know, well, whatever. I would say that they should have a form that looks closer to this one. But if you excite the supersymmetric one, it looks. Sorry, I should have put them.
I see.
Looks more like
that's
this
interesting. Yeah, okay.
Yeah, like that you can see from CFT analysis, in the sense that the Cardiff formula or this extended version of the Cardiff formula tells you that the answer should be a product of vacuum characters in the dual channel for the left mover and right mover. And then it's a question of which one is dominating the temperature dependence. Is it the right or the left? And if it's the supersymmetric one, you will get this answer. And if it's the non-supersymmetric one, you will get the same as the
I see.
The bosonic gravity theory.
So for near horizon extremal curve, for example, you expect it to be different, not to have a gap. I mean,
yeah. If it's not near BPS, I expect it to.
I see. Because near horizon extremal curve is actually not near BPS, but still, I mean, even there you can build an asymptotically neck with a cap in the infrared, which has a gap. But okay, we only have one solution, which was built by my student, by my.
Yeah, it will be. I mean, yeah, okay, it will be interesting to decide whether one of us is wrong, or maybe there is some reason why this is valid when you have like your construction is valid when you have supersymmetry, but maybe there is some extra effects when you don't have supersymmetry. Or maybe I'm wrong. I don't know.
No. It's very interesting that the fact. I mean, for me, the shocking part is that you can see a mass gap by just doing. I mean, you have a mass gap by just doing, pure ADS2 without a cap. Normally, we could only get the mass gap by capping the geometry, and then you solve the wave equation and so on. In the black hole solution, you could never get the mass gap. So the fact that you guys are getting a mass gap, it's amazing, and it comes out at the right place. So that's quite. Yeah.
The thing I'm sort of learning from this is that there are all these really cool, interesting saddle points that you get, but the connection to the Lorentzian theory is, there's startling coincidences and startling things that occur, like this gap, but it's sort of like a Euclidean saddle point in search of a Lorentzian theory. And the discussion we had earlier, which was what are the corresponding matrix? Actually, I see Clifford's turned up. Maybe he can answer the question. I was asking about matrix models that correspond to the more supersymmetric 0,4 super JTs and 4,4 super JTs. And, I remember from way back, there were issues of trying to get more matter into matrix models. So is there any kind of known sort of matrix model that gives us or captures the 0,4, 4,4 super JTs?
Oh, I see. Yes, I think I heard your question earlier.
I didn't see you were here though. So.
No, it's fine. I didn't have anything constructive to say, so I remained silent, and that's still the case. I don't see an obstruction. You mentioned something about it, maybe being connecting to the old C equals 1 barrier. I don't see that connection. But what Joaquin has already said is that indeed the n equals 1 cases are well understood. But I don't see an obstruction in principle to doing more. I think we're still learning. It's only been a couple of years, but maybe I've missed something. And Emil,
yeah, well, I think
what I mentioned, I don't know but just to see if you agree. What I mentioned is that I think there is not much information about the Bell-Peterson volumes to do something like SSS.
I agree, but what I'm saying is I don't see. There seemed to be some suggestion earlier that there was some grand reason why it wouldn't be possible, and that seems a stretch to me, unless I've missed something.
Well, I would say the only thing that we currently understand at the moment are what you would call type 0 theories. Right, the usual matrix model that's dual to n equals 1 supergravity is some analog of a type 0 theory where there are no space-time fermions in the game. It's all just bosonic observables. And so I think the main obstruction to getting something like what Nick wants is to understand how in a matrix model you incorporate things that are fermionic in space-time.
I agree. And I don't see any reason why that's not possible. I just think we haven't been smart enough yet.
That could very well be.
Yeah.
But yeah, one needs something analogous to a type 2 matrix model.
Exactly, yeah. And I think there are hints of those kinds of matrix models in the literature, but they're just sort of difficult to work with. And they haven't been upgraded yet to the current context. I had a question related to the exchange that Josef and Joaquin were having just now, and it's this slide. Was Josef seemed to be saying that you can construct the spectra that look roughly like the ones written here, sketched here. And so my question now connects to the discussion from yesterday, which is, can you enumerate that spectrum using these techniques and see whether there's the chaos? So the matrix model will tell you what the individual states are at the microscopic level that give you that profile, and you see matrix model statistics, which tells you have quantum chaos. Can you do that or see some hints of that? Or is there a calculation that suggests itself that you can do in order to see that using the fuzzball geometry approach?
So one thing, I guess the question is more for me than for Joaquin. One thing, so what we can do, we can take a superstratum of the type which discussed and so on, and then on top of the superstratum, we can build the tower of excitations. Now, for some reason which I don't understand, the gap between the superstratum, the supersymmetric solution, which again should be in this delta function here, and the non-supersymmetric first state, second state, and so on, the gap between the supersymmetric and the first state is of order 1 over n with some coefficient. And then the gaps between the states 2, 3, 3, 4, 4, 5, I mean, all the rest of the tower is actually equally spaced. We have no idea why, but this is what comes from just solving the equations of motion. We have no idea why, and those are horrible solutions which depend on 5 variables. So you don't expect any sort of regularity. Yet when you go from the ground state to the first state, there's an E gap, which is of order 1 over 2, actually it's 2 over n1n5 to be precise, and it matches exactly the one in the CFT. And in the CFT, this is just a closed string coming in, breaking into 2 open strings, going on the thing on the long string and coming back and being emitted. So this we know very well. And then you start seeing on top of every supersymmetric superstratum a tower, and every tower is again spaced at level 1 over n1n5, but with different gaps. The gaps are different. The gaps, in some 1, 0, n superstratum, the gap is something. In the 2, 1, n, the gap is something else. And all the superstrata we build, when you solve this thing numerically, you get some gap, which is some random number. When you solve them analytically in the larger limit, again, there are some numbers which are different. So all the superstrata, all the supersymmetric guys, which we basically have, which are again here in this spike, in the graphic, all of them have states on top of them. But again, on one superstratum, there's a state here. There's another one which has another state here. Maybe there are a bunch of them which have higher states. And then, of course, when you go to higher energies, all the towers on top of every superstratum, they start overlapping and coinciding and so on and so forth. So you start seeing a very dense forest of states here. In a sense, here there'll be some forest of states which come from various superstrata.
So just to jump in there, so you're saying they can, when they combine all the superstrata, states can get arbitrarily close. So I'm not getting the analog. I'm not getting the analog of eigenvalue repulsion. I see.
Indeed. So the point is, when you combine all of them, again, there's a tower on top of all of them. I have no idea again why the tower is the way it is, because again, from 0 to 1, the tower is there's one gap, and then from 1 to 2, 2 to 3, and so on, the gap is different and equal. So I have no idea why this happens. You know, maybe this is something which
can I clarify this because there's more data that's relevant. Joseph's talking about non-back reacted modes and the supergravity around a particular gravitational back reaction. That's our background. When you turn on the back reaction between the modes, you actually cause these excitations to interact with one another. Then the spectrum can go all over the place. And in particular, there are nonlinear corrections to the mode spectrum. So if I excite a mode over here, it changes the energy of a mode over here. So everything Joseph just said is about non-back reacted zero temperature superstrata. I think there's going to be a much, much richer structure in the non-BPS story.
So
even in the BPS story,
calculation to be done.
Sorry?
Or is it in principle possible using your techniques to somehow try to include the back reaction and to see if there's some scheme in which you could get a chaotic spectrum emerging, or maybe also, you know, sort of sneaking, you know, cheating and looking, you know what the answer might be, and whether that might give you some guidance as to how to do that kind of calculation.
I have two answers to that question. We made the first with Bogdan Ganchev and Anthony Hook. We made the first baby steps of doing that. It's a very Rube Goldberg calculation. You'll see it on Thursday. But the other thing also is that we've managed to dimensionally reduce the superstrata down to an effective three-dimensional supergravity. And you can actually reduce on the throat, I believe, to actually find the JT or super JT degrees of freedom. This is why I'm obsessing on the super JT, is that inside the superstratum, there are restricted classes of superstrata that will descend to a super JT. So, but it does require the activation of another degree of freedom, which is not in the JT spectrum. It's this so-called superstratum mode that so there is a way to actually take the kinds of models that Joseph and I are doing and make a direct connection to at least super JT.
But I think Clifford's question was a bit different. Clifford, can I also
hang on a second, Joseph, let Clifford say what
I think he had a different question, but that's what I understood.
No, go ahead.
So I think your question was, can you get on top of one superstratum? There's a question. Can you get a chaotic spectrum?
No, I don't know enough of your language to be that specific with my question. I was asking the more general question, and I think I think it fits with what Nick was saying. I think you're saying if you just have one, then and you look at the excitations on top of that, you're only looking at a piece of the story. So there's no reason why you should expect a chaotic a spectrum. It would be like looking in the matrix model side. It would be like focusing on some subsector of the eigenvalue spectrum, and wondering why you don't see things like eigenvalue repulsion. It's because you haven't considered all of them. So that I think you need to have all of the superstrata together, and then fully back reacting, and that would. And that would be fully back reaction going on. The 6-year-old wandering the corridors. So I think that makes sense. So it just seems that there's an interesting calculation that would be of interest to both communities, which would be to somehow see maybe in these models if some sort of back reaction inclusion could begin to see the kinds of features that we think should be there generically for other reasons, to do with JT and matrix models and things like that. But there's a question before back reaction. Back reaction is horrible. So there's a question one can ask before back reaction. If you just look at tiny way above E gap, so there's an E gap, and you basically have a huge amount of energy in the left movers, and then you're putting a tiny perturbation, you should still be able to get the spectrum which Joaquin has here. You should still be able to get the spectrum by just looking at perturbations, at least the slope. This is at least the slope, or maybe even the spectrum. You should be able to do that without doing back reaction. That's very nice, but that doesn't tell me anything about chaos. And my question is about chaos, right? I have the cinch form, but then I also have that cinch form is just an approximation to an underlying microscopic spectrum, which I know is chaotic. And that for me is a very interesting. Where do you expect the chaos?
If I might add a interpolation, you're not going to see eigenvalue repulsion without taking into account the non-linearities of the problem, I think. Is that correct?
Which comes from the back reaction.
Exactly. So yeah. There are non-linearity back reaction that's going to be essential to seeing any analog of eigenvalue repulsion.
Yeah.
And that's
so
why
I think Yeah.
Go ahead.
I'm just saying, I think this is an interesting set of calculations that could be done, perhaps using your techniques, which would be just a different approach to maybe landing at the place that we've arrived at on the JT side. That would be really interesting. That's all I'm saying.
Can I say something provocative about the JT side? I'd like to see what the answer is. You said a word a moment ago about saying you know the states. The thing about the beautiful thing about the matrix model calculations gives you the spectrum, but it's this issue of what are the states? What are you counting? I understand, but I'd say you haven't got the states, but you do have the spectrum. That's the clue you've got. Do you have more than the spectrum from the matrix model?
But what do you mean by more than the? I mean, the matrix model gives you the individual statistics of every state, of every the energies.
Except it doesn't tell me what I'm. Okay, well, it doesn't tell me what I'd like to look at a Lorentzian field theory and say, okay, here's my Lorentzian field theory, which this thing is counting these statistics of those.
Can I just suggest something? Sorry, Nick, to interrupt, but I think we're halfway out over the time limit, and I think we should continue this offline off YouTube, and I think we should ask. I think we should thank. Yeah, Joaquin
yes,
again.
indeed, Joaquin. Thank you very much.
I'm sorry for.
No, it was a great talk.
No. You're keeping the